Ladies and gentlemen, good morning, and we will begin the first keynote speech right now. And the chair of this keynote speech is Professor Vincent Zheng. May I ask you to give him a big hand? Thank you.
Good morning, everyone. It's my pleasure to chair this keynote session. Let me give a brief introduction to the keynote speaker, Dr. Zihua Zhou. Dr. Zihua Zhou is currently a professor and standing department director of the National Key Lab for Number Software Technology in Nanjing University. Professor Zhou is a pioneer in the fields of machine learning and data mining. He has published numerous papers in many patents, as well as a very popular and well-known book in several methods. Also, Professor Zhou is very active in international activities. He has served as chairs for a number of top conferences, and also the chair for IEEE DMTC committee, and also a number of active services. And also he served as editor-in-chief and also editors for a number of top journals, including IEEE Transactions on Knowledge and Data Engineering, and so on. He also won a lot of awards, including a number of best paper awards in winning conferences. Currently, he's a fellow of IEEE, IAPR, and CCF China, and also the ACM Distinguished Scientist. Please join me to welcome Professor Zhou.
So good morning, everyone. I want to thank the organizers for inviting me here, and thank Vincent for the generous introduction. My background is machine learning, so this talk is a machine learning talk. May I ask the first question, how many people here know machine learning? Would you raise your hands? Oh, thank you. Okay. Then, at first, please allow me to use one slide to give a very brief, very short introduction on what is machine learning and what is a typical machine learning process. In many applications, we may collect a set of data. For example, suppose we organize the data in a formula or table. Here, each row corresponds to one object or one real event, and each column corresponds to one attribute or feature describing this event. For example, this tuple says a person named as Mike, and his rank is assistant professor. He works for 3 years, and with his tenure note, his no tenure. So this, with the tenure note, we call it as a label. This is what we want to make a prediction in the future. Then after we get this kind of data, we call it as training data. Then after training process, we can get a training model. With the trained model, in the future, once you receive some new data, for this kind of new data, you only have the input. You do not know the output. For example, we know there are a person named as Jeff. He's a professor. He has worked for 7 years. Then whether his tenure or not, we do not know. Then we just input this instance to the model. Then the model will give you the answer. So you can see almost any kinds of prediction, classification, such kind of tasks, once you abstract to consider it from abstract level, then this is a machine learning program. So the key is how to transfer from the data to the model. We need to use a learning algorithm. So if we see computer science is about the sense of algorithms, then the machine learning is just to try to study the design, application, and analysis of the learning algorithm. So in all of my talk, we will focus on how to construct a better learning algorithm such that you can have a better model from a given set of training data. So this is what we do with machine learning. So nowadays, in every day, we are heard something about big data, and this is a buzzword. And there are many people try to analyze what is some new aspects brought by big data to intelligent analytics or machine learning. And there are many discussions. Some of these discussions may bring some new aspects, some are not really new. Some trends actually have appeared more than 10 years ago. So we have quite a lot of discussion paper last year published by Tribune Conventional Intelligence magazine. And in this paper, we analyzed there are some new aspects, and some new aspects are not as new as many people expected. So today, I will just talk about one issue. This issue is what we believe is really brought by big data as a new challenge to machine learning or any other kind of data modeling if you want to handle big data. So let's go back to the figure I showed you first. As I have told you, what we want to do is to construct a good model from the training data. But at first, you need to ask one question: what model is good? So in some case, we want to see that when we want to construct the model, we did and we hope the model can be very good in processing future unseen instance, unseen data. We do not just want to use this model to explain the data we have already observed. We hope we can use the data to make good prediction on the future. But what prediction can be said as good? Actually, this depends on what performance measure you will use to evaluate the performance of the model. So in other words, whether a model is good or not does not only depend on the model itself. It critically depends on what performance measure you will use to evaluate the performance. So in machine learning, during last decades, we have got this kind of common sense knowledge. That is, if you really know what you want to get, if you know what you want to use to evaluate the performance, then you can just take the function response to the performance measure as an object. Then you just try to optimize the objective. Then finally, you will get a model exactly work well on the performance measure you want to optimize. So this might be relatively more complicated, but you just think that we are using some data to do something. If we advance, we can know finally what I want to do and what is good for me. Then I can just write the target as a function. Then I just let the learning process to optimize this function. Then finally, you will get a very good model. So for example, if we just care about the small number of mistakes, I hope that in the future, when I make prediction, I want to reduce the number of mistakes. Then you can just try to optimize accuracy. The accuracy means if I give you 100 samples, if you make correct prediction on 90, then you have an accuracy of 90%. Then you just try to optimize this measure, then you get this result. In information retrieval tasks, usually we care about both precision and recall. If you kill both of them, then in this sense, you optimize accuracy will not bring you to a good performance. In this way, we can try to optimize F1. So as you can see, we have many different kinds of performance measures. So it's not that simple. You just pick one performance measure, then optimize it, then you want to have a good performance. This is not the truth. Actually, you need to pick the right performance measure. And once you can pick the right performance measure, we can take it as an objective function. Then you just try to optimize this objective function. So that's the task. So but today I want to see that previously people all know that. And what can we do? Typically, we collect all the data and then do the optimization. But nowadays, given the rise of big data, we have more and more data. Then get all data, then optimize. This might be infeasible. And it's more serious that in many big data applications, usually the data is accumulated with time. For example, the first time when you start to train the model, then you just want to have one big size data. And when the model is in use, you increasingly collect more and more data. Then in this sense, you can never collect all the data, then construct the model. Then what can we do? So the answer is very simple. We just try to do incremental learning. So by incremental learning, we mean that At first, you have some data, and then you use the data to train a model. Then the model can be used. Then you can receive some new data. But when you receive new data, you do not need to collect all the data and then retrain the model. You only need to use the new data to adjust the existing model. Then the model can become better. So this is incremental learning. So a very important property is, if you can do incremental learning, then once you train a model, then all the data can be discarded. Then you just get some new data, then use the new data to train the model. So you can see this is really what we want when we want to handle big data. Because in big data application, it's very, very difficult for you to collect all the data and store them. Usually, we can only store a part of them. But for machine learning, if you just store a part of data, then you will have a very big challenge. When you have some new data and use the new data to adjust the model, how can you prevent the knowledge learned before be washed out? So this is a real challenge. So incremental learning is very, very difficult. But this is what we want, what we really want. If we collect incremental learning as to what we have mentioned before for performance measure, you will find that the task is actually very, very challenging. So if we take a look into some popular performance measures, you can see there are some performance measures with good property. For example, accuracy. The accuracy, as I have mentioned to you, this is measured as I give you 100 sample. If you make a correct prediction on 90, then your accuracy is 90 divided by 100 is 90%. So if you write it formally, you can see this is the ground truth. This fxi is what we make prediction on xi. Then if the ground truth equals to what we predict, then you have 1 point. Then we consider all m samples, then family, so this is the expression of accuracy. When we want to optimize accuracy, you can see we just take a maximum of this equation. So you can see for this equation, it has some very good property. The first is this can be considered every example one by one. So we see it's decomposable over examples. So this is a very good property for incremental learning. Because at first, if you have 100 samples, you have a model. Then once you receive new data, if it's correct, predicted, then the accuracy just add 1. If it's worse, then you just minus 1. So your calculation of performance measure can be decomposed into every sample. So this is very good. And moreover, they have many convex surrogate losses such as H loss, collision loss, and so on. So the optimization is easy. But in many real applications, particularly for big data applications, usually will suffer from when we need to calculate information retrieval and so on. The performance measure does not have these good properties. Usually, they are non-decomposable, non-linear, non-smooth, non-convex, and all of these properties are very, very bad. And if we just collect all the data and then do the optimization, for example, F1 score, PR, big map, AUC, this is already very challenging. Needless to say, if we just want to do incremental optimization on these performance measures. So in this talk, I will show you recently how machine learning community has made this task become feasible. I will take AUC as an example to show you how this kind of complicated performance measure we can really do incremental optimization. And behind this is some very important theoretical recognition of some premise, very good lossy functions. So I will take AUC as an example, but all the ideas in this talk can also be generalized to other performance measures. So first, let me explain to you what is AUC. So let's look into this figure. So the horizontal line, the x-axis, is false positive rate. So the false positive rate means the false positive you make prediction divided by the number of negative examples. For example, in two-class classification, we can have one class is positive, another class is negative. Then how many negative examples you have? This is m minus. Then how many negative examples have you mistakenly predicted as positive? This is false positive. So this means these are bad guys, a set of bad guys. But if you mistakenly believe some bad guys is good, then this is false positive root. So we can see ideally we want to have the false positive root is 0. So may I explain the false positive root again? So the false positive root means how many bad guys have been mistakenly predicted as positive as good guys. So this is, of course, we want the false positive root to be real. So ideally, we have this point here. And the vertical line is the true positive root. The true positive root means how many good guys have been really predicted as good guys. You know, gives you some sample. You will make some prediction. Because the sample you do not know stable before, then you may make a good prediction or bad prediction. For good prediction, then you are correct. For bad prediction, there are two kinds of mistakes. One mistake is a good thing you mistakenly predicted as bad. Another is a bad thing you mistakenly predicted as good. So this horizontal and vertical line just show this kind of fact that you make mistakes in two ways. So this is what you make. Negative, negative. This is a correct and positive. But if you want to use one subject, this one you get. What you make mistake and positive. So you can see the true positive rate ideally should be this point. So if for an ideal perfect classifier or perfect model, what we want to have is a point here. But actually, in real practice, we can never reach. Very difficult for us to get a perfect classifier. So usually we could not get this point. Usually we'll get a point in this plane in some places. But if you have trained some data mining or machine learning algorithm, you will have the experience that there are many parameters for you to set. If you set different parameters, the performance might be different. So if you set different parameters or using different size of training data for the same algorithm, you might get multiple data points here. Then once you collect all these data points, you will get this curve. This curve is called ROC, road curve, a receiver operating characteristic curve. This curve was invented in World War II. People at that time used this curve to help to diagnose some information from the radar signal to identify whether some attacking enemy flight coming or not. So in this way, we do not want to mistakenly, if there's no enemy flight, we will do this very small. And we really want to identify all the real enemies. So we want to have this. But frankly, you usually have a curve if you collect all these data points. So we can see for any one algorithm, if we do not know how we will set the parameters, we can use this curve to express its performance. So the area under this curve is called AUC. So you can see the AUC actually express the expected performance of an algorithm. So if we want to see that algorithm is better, then we usually will see the AUC should be bigger. So in other words, the bigger the AUC, the better the expected general performance of an algorithm. So do you have any question here? Please feel free to raise. So to understand what is AUC is very important for the following. So the AUC is just the area under this curve. So this performance value is very, very important. It expresses expected performance of an algorithm, or overall performance of an algorithm. It's not just a single data point, how you set the parameter. If you set different parameters, the performance is still captured by this performance. So in the later part, if I mean we want to optimize AUC, what we mean is we want to maximize this region. So there are many algorithms want to do to maximize this region because AUC was invented in 1970s. And later on, many researchers use this important criteria. And this performance layer has many good properties. First, it ranks positive instance higher than negative ones. It's insensitive to class distribution. It's independent of class fiction threshold. So it has been used in various learning tasks, such as learning to rank, class invariance learning, cost-sensitive learning, and so on. So, but I want to mention that to optimize AUC is very, very challenging. This is because, let me show you the function. If we formally see this function, then suppose we have a data sample size, S, and we have n plus number of positive examples, and n minus number of negative examples. Here, positive 1 means this is a positive example. Negative 1 means this is a negative example. Then the AUC is just given by this function. So you can see the first part is I pick one positive example, and I hope the prediction of the positive example is smaller than that of a negative example. In other words, all the positive examples should rank higher than negative example. If you rank lower, then you will receive one penalty. If a positive and negative are ranked as the same, then you will receive 0.5 penalty. Then finally, you just want to minimize this part. So let me show you this figure. So this is actually the AUC function. So we can see we take a pair of instances, one positive and one negative, and when we calculate the corresponding difference between the outputs. Then, if the positive is bigger than negative, then you will receive 0 penalty. If the positive is smaller than the out of negative, you will receive 1 penalty. If they are equal, you will receive 0 penalty. So what we want is just to minimize this function. So you can see this function is non-continuous, non-smooth. The property is very, very poor. Then how can we do? So previously, people just try to use a surrogate loss. A surrogate loss means that one function is very difficult. Then we can hardly do this function directly. Then we pick another function. We hope that when the other function reaches optimal, we also reach the optimal of the original function. So previously, people usually use this kind of functions. Exponential function, hinge loss, exponential loss, and so on. And almost all the previous AUC optimization algorithms are based on these surrogate functions. So you can see when the hinge loss reach optimal, we reach here. When the exponential loss reach optimal, we reach here. But these functions are continuous, differentiable, and they have good property. So we do this. So this is the background of AUC and AUC optimization. Now I come to the very critical point. So you need to know that the very, very different part of AUC is that it's a pairwise loss. To calculate AUC, we need to consider two data points simultaneously, one positive, one negative. We need to consider a pair of instances together. So this is very different from accuracy. Accuracy, as I mentioned to you, you only take one sample to see whether you make an error or not. Now you need to consider a pair. So you can see, if we need to consider a pair of points, then you have to store all the data. If you do not store all the data, once you consider one new data, how can you know the relation between this data and some data outside of storage? It's difficult. So if you consider pairwise data, pairwise loss, you need to store all the data. And on the other hand, because for each new data, you need to consider its relation with all the existing data. You need to scan the data for many times. So right? Do you understand? Okay, so these are two very important issues. Consider pairwise loss, because you need to consider two samples simultaneously. Then that means you need to store all data. Otherwise, if some data are out of the storage, once you have some new data, how can you consider relation between the data inside the storage and outside the storage? It's not possible. Another is because for every data you need to couple it with all the previous data. Then that means you need to scan the data for many times. So you can see, if you consider such kind of pairwise loss, if you have very big data, the problem itself is very, very inhibited for you to use big data because you can hardly store all data, and it's very costly to scan data for many times. So this is very challenging. Then consider that we have big data application and we really want to optimize AUC. What we can do, as I have mentioned, we just want to do incremental optimization. But this is very, very difficult. For a natural idea of incremental optimization is we run online learning using statistic gradient descent. Online learning means that we just assume the data coming one by one. Once we receive a new data, we will do some justification based on the new data. Then statistical gradient descent means once you have a new data, you calculate how the gradient change will be brought by the new data. Then you just add this part to the original one, then you finish the update. But if you consider a univariate loss means each time you consider one sample. This is simple. This is all people done before. But now, if we consider pairwise loss, as I have mentioned, you need to consider a pair example. This will become infeasible, at least from all the private solutions infeasible. Then how to address this issue? A very natural heuristic idea is, if I consider all data, then I can hardly store all data. Then how about I just select some important data? This important data can be held in your storage. Then once you receive a new data, I do not need to resort to the whole data. I just consider data inside the storage. Then the problem can be addressed. So this is a very natural idea, and this has been reported some years ago. The idea is simple. Suppose we have a set of positive and set of negative. You just do a sample, have a sample of positive, sample of negative. But you need to guarantee that these are important sample. And then, when you receive new data, because all the important samples are inside the memory, then you only need to calculate the new data with the sample inside the memory. Then everything adjusts. So theoretically, it can be proved that if you can set the buffer size in square root n plus n minus, n plus is the number of positive instances, the n minus is the number of negative instances, then you can have a very good performance. This is have a theoretical guarantee. So, but does this solve all our problem? This is not the fact. This is because for you use this kind of a buffer strategy, you need to know how many positive examples and how many negative examples you will receive finally. So as I have mentioned to you, in many big data applications, the data is accumulated with time. At the starting point of the data application, we even do not know how many samples I will have. Needless to see, if I just want to know how many positive and how many negative examples I will receive. Then, if you do not know this, you do not know how can you set this buffer size. Then all the theoretical guarantee will go away. So this means this is not a very good solution. So let me go back to show you a revisit of all the approach before. The current approach for optimized AUC is either want to store all data and scan all data for many times, or use a buffer. The buffer is dependent to data size, and you still need to scan the buffer for many times. So this is not what we want, because for bigger data, buffer size still will be big. And for streaming data, we even do not know how many instances we will receive, and difficult to decide the buffer size. So what we really want to have is, we call it as one-pass approach. By one-pass approach, we mean we only need to scan the data once. Once you receive the data, you scan it, then the data can be discarded. Then in this way, no matter how big data you will receive, you can use a fixed, constant storage. And another is, we do not hold the storage dependent to data size. We just want to use a storage. If you need to store some middle results, we hold the storage independent to data size. That means if you just want to have 1 million sample, or 1 billion sample, I will use a fixed storage because I only need to scan data once, and what I store is a fixed constant. So we can see this is what we really want. But if we consider a pairwise loss, the AUC need to consider every pair example, you will see how this can be possible. If you scan the data once, then if the data received you have discarded, then when you receive a new data, how can you calculate the relation between the new data and the previous one? The previous one has already been discarded. How can you do that? So these things are mission impossible. But it's amazing is that we found that recent theoretical results show that this is possible. So let me show you. We propose a very interesting approach named OPAC. For this approach, it really reach our goal of one-pass AUC optimization. This is a 3-step, 3 key steps. The first is we prove least square loss is consistent with AUC. This is possibly the most important part, the most intriguing factor we found. Then we derive that for AUC optimization, though from the previous introduction you can see it's very complicated, we can show you only need the 2 statistics for a very incremental, very efficient update. Then finally, we will show you OPAC approach, and still there are some trick here. So first, the most important result is we prove that the least square loss in this way is consistent with AUC function. So I will not go into the theoretical details. It's very boring for you, maybe. I just share with you some intuition. When we talk about consistency, as I have introduced to you, the target is very complicated. The target function, AUC function, is very complicated. So usually we do not try to optimize it directly. Usually we will take another function. The other function we call it the surrogate. We hope that when we reach the optimal of the surrogate, at the same time we reach the optimal of the original target. So this is consistency. Then if we can find some function with a consistency property, then we can use this function as a surrogate for the optimization of the original target. Okay? So this is proof. I will not show you. But the least square loss is very popularly used 50 years ago. When people do some statistical analysis, for example, maybe the least square method for regression, they use least square loss. But after statistical learning rise up, the least square laws have not attracted more people because most people go to hinge laws, exponential laws. And those people thought that least square laws can be consistent with AUC function. Why? You just look into this figure. So you can see this is AUC function. This is square laws. So the AUC function tells you that when the output of the positive, the bigger than negative, then you will receive zero penalty. No matter how different the output is, given that the positive output is bigger than negative, you should receive zero penalty. But for square laws, you can see it goes in this way. That means after some point, if the positive is much bigger, then you will receive some penalty. So you can see this and this are very different. This part is not what we want. So theoretically we say that this function itself is not consistent with this function. But how can we show that these square laws can be used? We have a very important condition. The condition is we want to do stochastic gradient descent. Because we want to do incremental learning. Once we receive a new data, we hope to derive this gradient. Then we just calculate the gradient to update the original one. In this way, we want to gradient descent. So for gradient descent, if you have some data point here, you will go down. Once you retrieve the minimum, the level goes up. So in other words, if you use gradient descent, the right half part of square laws will never be used. So if you only consider the left-hand side, then it's consistent with AUC function. So that means our finding is that if you use gradient descent in your solution, you can take least square laws as a surrogate. Then you can try to optimize this square loss. And finally, the optimal exactly corresponds to the optimal of the AUC function. Then, based on this finding, we can use this square loss. This explains to you why use this square loss is very good, because this square loss have very, very good property. As you know, for stochastic gradient descent, if you have Wt, to get Wt plus 1, we only need to calculate the gradient. Then if you take the square loss as a function L here, just try to calculate the gradient. It's very simple. After some simple algebra, we can write the subgradient in this way. You can see this is the mean of lattice sample, mean of lattice sample, mean of lattice sample, the covariance of lattice sample. Then you can see for all the updates, we only need to store two statistics. The one the mean, the average, another is covariance. No matter how big the data is, you only need to store only these two parts. And these two parts is very small. And how about the update? The update is very, very simple. You know how to calculate the mean. This is the total amount divided by the sample size. Then suppose you have already 100 samples of the mean value. Given one new sample, you just use new sample divided by 1001. Then add this to the previous one. Then that's done. So this is update of the means, very, very simple. You just only need to do one vector addition. To update covariance is also very simple. You just need to do 4 matrix addition. So this theoretical guarantee that by using this square loss, you can have a very, very efficient algorithm can do incremental optimization. Now we have this algorithm. Now suppose you receive a new training example. If it's positive, then you update the mean and the covariance matrix of positive instance, then calculate the gradient. If selective, then update the mean and covariance corresponds to selective instance, then calculate the gradient. Finally, just to do this, the gradient updates, then finish. So you can see what we need to store is a mean and the covariance matrix. For mean, suppose you will use a D number of feature to describe one instance. You will just store OD. For covariance matrix, you need to store D squared. So you can see D and D squared have nothing to do with the sample size N. So that means the storage is independent to data size. And moreover, we only scan the data once. Once the data you receive, after update, you can discard. So you can see this algorithm reach our goal of one pass AUC optimization. So once we have this algorithm, all our premise, our real goal has been reached. But in order to make this algorithm very, very practical, we still want to address one issue. This issue is now the storage is still related to the feature number D. You know, in many applications, D is not very big. For example, you just have 1,000 features, 2,000 features, okay. But in some application, for example, in micro data, maybe you will have millions of some features. Then the D will still be very big, D squared. Then we hope to address, if we have large D, we can still work with how to handle large D. So for this, there might be some very simple idea. Maybe you can do some feature high dimensional data process. For example, the dimensional data dimension reduction or random projection. For example, random projection is very simple. For high dimensional data, you just randomly select a part of low dimensional data features, then you apply the algorithm on the low dimensional data. But I will show you that all this method does not work. Even for dimension reduction, if you run dimension reduction at first, then you apply the algorithm to optimize AUC, it does not work. Then what we propose finally is this kind of solution. Suppose the D times D squared matrix is very big. Then finally you can use a small size matrix to approximate. So this is a kind of low rank approximation of the matrix. This kind of idea has been studied many years. For example, when you have a large scale SVM, you want to reduce the size of the small vectors, you can run low rank approximation, matrix approximation. then you store a very small data matrix, then you can recover this one. So we call this algorithm as opaque R. This uses low rank approximation. So let me show you some theory results. In theory, we can prove that for the worst case, the performance, the convergence rate is 1 over square root t. Well, previously, the best case is 1 over square root t. And this is separable data, and this is a non-separable data. So theoretically, you can see the opaque is very, very good. So I will not go into these details. So I just show you some aggregate performance. So first, we run some experiments on some benchmark data. These data are scanned from several hundred examples to 500,000 examples, the feature from 2 to 2,000. So we compare with a lot of algorithms. These are two incremental, but with buffer-based methods. These are 3 batch mode methods. So for this method, you collect all the data and then do the optimization. So first, if you compare with the online methods, which based on buffer, here the black dot means the new method works significantly better. So you can see the win time loss count show the new method win 40 times and never lose. So you can see compared to the buffer size, buffer-based method, this new method is significantly better. And more amazing is if we compare with batch mode methods, for these methods, they need to collect all the data at first, then do the optimization. You can see the win, tie, loss counts are comparable. So in that words, for all these batch mode methods, although they need to scan the data for many times and store the whole data, where opaque only scan once and store only statistics, but the performance is almost exactly as good as the batch-based methods. So in the future, no matter how big the data you will have, you only need to store a mean and the covariance, then scan data once, then the performance you will retrieve is almost as good as the batch-based methods. So this is because we have theoretical guarantee. Theoretically, you can guarantee you reach the optimum. But when you have very, very high temperature data, so this is other comparison I will not show you. Other comparison just to see the same. If you have very, very high temperature data, now we need to use low rank approximation. We run these experiments. The features from 20,000 to more than 1 million features. Sample from 10,000 to 500,000. So the feature number is very, very high. Then you can see the first row is all methods. These small 3 rows corresponds to high-level data process. These methods, at first you run random selection, random projection, and using PCA to do the dynamic reduction. But all these methods does not work. You can see there are a lot of black dots here. So in the middle, there are some other methods. So you can see there are some very interesting phenomena. To the left-hand side, there are a lot of black dots. The right-hand side, the black dots reduce the number of black dots. If we just write the diagonality here, you can see there is a very clear boundary. If your data has more than 50,000 features, then by using low rank approximation, you will have a big benefit. If your feature number is smaller than 50,000, then the performance benefit is not very big. So in other words, in our paper published 2 years ago, we show that if you do not have high-level data, you run our proposed standard algorithm, then you will reach the optimum. This is have some theoretical guarantee. If you have a feature more than 50,000, then by using low rank approximation, you will have good performance. But if your feature is from 10,000 to 5,000, the result is confused. Yeah.
So we have the sharp boundary problem. So is it sharp 50,000?
Not sharp 50,000. This is just to give you observation.
Fuzzy.
Yeah. This is just an observation. I will address this later. Yeah. So this is what we have reported at that time. So later on, we will, of course, want to address this issue. We have to have a method which can work very well in the whole span. Then we go back to consider our solution. Now, for our solution, if you do not have very high dimensional data, we theoretically have already guaranteed performance. Now, the only issue is when you have high dimensional data, then we run low rank approximation. We found that this kind of optimization is needed. Otherwise, you can never hold D-squared matrix. But the problem is, we run low rank approximation is an area. There are many different algorithms. We have tried many of these algorithms, but we could not get a better performance. But finally, we do a step which we should have already done for the first step. That is, how about just simply keeping the largest d times tau entries? This is almost the baseline we should have run for the first. For example, for 100 times 100 square matrix, if we want to just keep 10 entries, the simple idea is we just pick the 10 biggest one. For example, this d times g squared, this is d times tau non-zero. We just pick the biggest entry, then set all these entries, the remaining entry as 0. So previously we did not run this because for all the study about low rank approximation, people will tell you that this kind of thing never work. And in all the literature, they will show you this kind of thing never work. But finally, we run this. Suppose we have this algorithm OPAC-S. Now we use this method. It's very amazing that this method works very well. Now you can see this is OPAC-S. Now no matter how big the dimensionality is, if you have high dimensional data, you just run this method. And it's consistently better than the method based on low rank approximation. So this is very amazing. You can see you have a big matrix, you just pick the biggest entries and set all the small entries as 0. So the computational cost is very small, much smaller than low rank approximation. But after do this simple step, the method with this simple step is even better than all the complicated algorithm, and it works no matter how big the dimensionality is. So this fact is very counterintuition, and is also contracted to all the previous literatures about low rank approximation. So we want to understand why. So we run these results. After you get low rank, the small matrix, you can try to recover the original big matrix and to see whether AUC value keeps or not. So you can see this is just a random pick, the biggest one entry. This is the error of low rank approximation. So you can see picks, the smallest, the biggest entry is always the best. The red curve corresponds to biggest entry. So OPAC-S seems achieving a better optimization of the covariance matrix. But to understand why this is fact, this remains an open problem. We have discussed this issue with many mathematicians, and they also feel very strange. And one possible conjecture is that because all the previous study about low rank approximation is based on accuracy, they guess maybe the property of accuracy and AUC is very different. Because for accuracy, we only consider one sample. For AUC, we need to consider two samples. Then this might be a kind of two-order structure. Then from the two-order structure sense of view, maybe the low rank approximation, all the previous results should have some other appearance. So this is just a guess. But if we can understand what is the reason behind this phenomenon, maybe we can derive some new, very effective algorithm in the future. So this part of the result we have not published yet. This is reported in the technical report in this year. So anyway, to here, I just show you that for AUC optimization, now we have good results for you to do one pass optimization. No matter how big the data is, no matter how high the dimensionality is, you can just try OPAC approach if the dimension is very high, you just do a selection of the biggest entries, then use this to the covariance matrix, then everything is done. So I need to briefly mention another thing. All the previous study, the key of the all-pack approach is based on the use of the least square laws. As I have shared with you that we show the least square laws is consistent with AUC optimization, but the condition is that you need to consider the stochastic gradient descent. But you may think that, how about I develop another solution? This solution does not consider gradient descent. Maybe I can use another solution, then this result does not hold. So I need to warn you that if you want to use other approach to do the optimization, if you do not based on gradient descent, then least square laws is not consistent. You should not use least square laws. Now the question is, what about the condition for AUC consistency in general situation? This has not been studied before. Previously, we have some results. For binary classification or any other kind of a single sample optimization, we can see if you want to have a function which is consistent, it must be calibration. Calibration means that the function should be convex and the one order derivative should be negative. If you have these two properties, then this is calibration. Then if a function is calibration, you can simply use it as a surrogate loss. This is previous result. But now, we prove that for AUC, all these kinds of pairwise laws, calibration is just a necessary condition. If a function which is consistent with AUC, it must be calibrated. But if you just do a calibration, you can never reach AUC consistency. Then how can you make a function for AUC consistency? We prove that you need to have another two conditions. First is the function should be non-increasing. The second is the function need to be differentiable. Then if you have these three conditions, the first, the calibration plus these two, then the function can be consistent with AUC. So that means in the future, if you want to use gradient descent, then you can use least square laws. If you do not want to use least gradient descent, if you do not want to use gradient descent, then you need to use a function which satisfies this condition. Otherwise, your results will never have any theoretical guarantee. So, with this new understanding, we will need to have some new algorithm. When you want to design some new surrogate laws, you just check these conditions. I will skip another thing, because it's very complicated. Let me share with you some technical summary of the beginning of this talk. For one-pass optimization, this is what we want to have for big data machine learning. That means we hope to scan the data once, and we hope that the storage is independent to data size. First, we hope that the pairwise, we show that pairwise least square loss is consistent with AUC. This is very important finding. And if you using gradient descent in the future, you can use least square loss. The second is, if you use least square loss, you only need two statistics. They are sufficient for AUC correlation. And finally, for high-level data, a sparse approximation of covariance matrix is very helpful. This is another part I'm not sure. So I also want to mention something. The incremental learning is a concept proposed in the early of 1990s, but later on it has not been emphasized. But nowadays, with the raising of big data, we believe incremental learning should attract more attention. But for incremental learning, there are actually three aspects. The simple aspect is example incremental learning. This means that once you receive data, you construct a model. When the model is being used, you will receive some new data. So this is data is increasing. We can have also some class incremental. For example, originally you just have two class data. You construct an algorithm, a model. But when the model is in use, you will receive some new class. then how to handle this scenario, and also attribute incremental learning. Originally, maybe I have just 1,000 sensor. I have just 1,000 features. When the model is in use, maybe we deploy more sensors. Then you have more features. Then how to use this new feature? So this is attribute incremental learning. Then also, almost the previous study about incremental learning focused on example incremental learning. And very few study about class and attribute incremental learning. About these two issues, we believe they should attract more attention in the future. And for class incremental learning, recently we have one work published in July last year, and if you have interest, you can check. This work involved joint work with my students Galway and some of my collaborators. So finally, I give you some take-home message. The first is, for big data era, incremental learning is important. The second is, least square loss is even more useful than before. Third part, because I have missed the second part, I want to show you relevant and previously trained model can be useful. And all the codes are shared. You can try to use it if you have interest. So that's all. Thank you.
Thanks for Professor Zhou's nice talk. I believe all of you, including myself, should feel very inspired and excited about this breakthrough results, which I believe will bring big impact for the big data analytics. Yeah. So we have time for a couple of questions. So any question? Yeah.
So you talk about dimensionality. What about if the dimensions are dependent or independent? How you handle the case when all the dimensions, let's say, are independent?
Sorry?
How you handle the case when all dimensions are independent?
Yes. This is not an issue for this algorithm. We have tried many data sets where all the features are important. There's almost no redundant feature, but I can still run this method because this method does not remove any feature. We do not remove any feature. What we show empirically is if you just remove some feature, then the performance will be poor. What we do is just to do some simplification about the covariance matrix. Originally, you have a long feature. You just can calculate the product of them, and then you have the covariance matrix. Then all the simplification based on the covariance matrix. This is good way. If you at first discard some original feature, no matter by feature selection, random projection, or time reduction, finally, from our external results, this will be very poor.
Other question?
Yeah, I just want to ask, especially for big data, they actually have a lot of data consists some uncertainty, maybe missing or even class maybe automatic. So I'm just curious for the incremental learning, is this issue has been considered, or can you give us some hint or your experience about this issue? Yeah, thank you.
Oh yeah, this is a very sharp question. Very good question. Actually, to handle missing data is another branch which is focused by data mining area. And for incremental learning, previously studied by the machine learning area almost 10 years ago. But nowadays, when we want to handle big data, usually the incremental facts we need, and we also need to handle the missing data. But if you check the literature, you can see incremental learning study with missing data is very, very few before. But this is possible. Nowadays, we know that there are several groups simultaneously now working on this direction. So this is a suggestion. I know there are many students here. If you want to pick some new direction to work, maybe incremental learning with missing data is a very, very good direction. This is not as challenging as before, we think. This because we still are able to do something very soon. But this is just because previously these two studies are almost in two different communities. And just recently, people think these two issues should be considered together. So many things can be done. So I believe in the next year, there are many such kind of results will be published. In my own group, we also have some study about this.
The result of learning is the model, right?
Yeah.
And because you are doing the incremental learning, so the model will change or not change.
Will change.
So you can find the final models from your incremental learning algorithm, or just find the major value.
We will get this model. The incremental learning means at first you have some data, you train the model. Then when you receive new data, you just use the new data to adjust, to modify the model. And then at every time you have a new data, you can have a new model. This model is different from the previous one. Of course, you can have a serious model. This depends on your application. Sometimes you need to have a serious model to keep on track of how the model change. Sometimes you only need the final model. So we have the model.
Your talk, I just find the final prediction result, but not the model change.
Yeah, we have the model. The model change because when we change the gradient, actually the gradient reflects the model. But when we evaluate how the model perform, we show the evaluation result of this model.
Yeah, okay. I think it's about time for this session. I think it's really a pleasure to have such a great talk from Professor Zhou. And just a very quick echo to this words done by Professor Zhou. Yeah. Actually, I myself has the opportunity for conducting some practical projects with some large corporations in Taiwan, and actually many of them have this kind of demands. Yeah, especially with their bigger and bigger data. Yeah, so I believe this incremental learning model will bring big impact, as we can see very soon. Yeah, so please join me to thank Professor Zhou again. We have some gift for Professor Zhou as appreciation.
Ladies and gentlemen, just wait for a moment. I have some important message to announce. First of all, if you are the council member of TASN, the Taiwanese Association for Social Networks, please move to the Council Center 103 to have your lunch and also attend the council meeting of TASN. And if you are a member of TASN, please don't forget to vote for the next member of council of TASN. And the lunch box, you just move outside and pick from the reception desk. And thank you. And next keynote speech will be held on 1:30 p.m. So please attend at this same place and back to here. Thank you very much.